Okay, so we looked at different estimators of sigma. I could have underlined that these are actually just estimators of sigma down here. So we use the weighted least squares estimator to get an estimator of the parameter, but we should not use it for theta because we have, as is written up there, our assumption about the residuals is not a weighted correlation structure that we have for the weighted least squares. We assume that they are the same. I proposed that estimator here to be a local estimator, and if you want a global one, you should do what is down here. Actually, as I mentioned to a few of you down here in the break, this estimator is not the very best thing you can do. But I will save you for repeating this on a blackboard. I don't know if you can see how much is in here. But that's a derivation of how many degrees of freedom do you actually have t minus p here. T is the exact value. P is not exactly that value, but it's close to p. And this is the best global estimator, the one that is framed down here. So those are the ones that I showed just before, where you look at, you make the one-step predictions, and you correct each prediction with the associated prediction error. And then you divide by how many observations did you actually take, how many predictions did you use. In my code, I used lowercase n equals to 2 here, but I mean, in a real-time application, real application where you have a sequence of observations before you need to start making predictions with intervals, I would pick n to be larger so that you avoid this burn-in period here in the first, say, 50 observations here. Because, I mean, except for the red line, all the other estimators are in the neighborhood of the true value after, say, 50 observations. And for practical purposes, maybe a 10, 15, 20% deviation is not essential. Often, you can say just getting order of magnitude is important. And I think the black points here are generally a little bit higher than the true value. But it's better to say that something is a little bit more uncertain than it is, than to say that I am 100% certain that this will happen, and then something different happens too often. It's better to say that I am fairly uncertain, and then you kind of get something that is in the center. But that again, that comes down to testing so-called skill scores and other things. That's just saying that we stabilize the estimator by ignoring the first few. So, what have we done so far? We've done some local trend models. Here I plotted the global trend model given data up to time 6, that's the black one, and data up to time 7, that's the red one, and then I made a sequence of local linear model predictions to time t equals 7, given information up to time 6. Now, the question is, which one of these has the highest lambda? Sorry? You say the lowest line. Why do you say the lowest line? Now, the higher the lambda, the more weight you have on the previous. Because you have the weight, oh, well, it's written up here. It's written here. Lambda to the j power is the weight that you have. then it's just the opposite. Exactly. So the top one, the one that is closest to the global linear model, is the one that has the highest lambda, the least forgetting. Whereas the bottom one here is basically just using a linear regression with most weight on those two observations. Okay, now changing to something totally different. What we have and where we will be going in the, you can say, the next quite some lectures, stepping away from weighted least squares and local linear model, starting to get into stochastic processes. What do we do? Well, first we need to define so-called operators. I think you are familiar with one kind of operator, namely the differential operator. So you take the differential of some function or something that you are familiar with. What we're doing here is something similar, but we're just changing time. Yeah, I was speaking too much in the break. So, an operator here is a function of a time series, or a stochastic process. That you can say basically just the definition of, do we know xt, or is it actually just a stochastic process that we haven't observed yet? Whenever you apply an operator on a time series, you get a new series out that is somehow different. What we'll spend the most time on is the backward shift operator. B, when it acts on, say, stochastic variable xt, what you get out is the one where you just change time one time step. So it's a backward shift. You shift time backwards one step. That intuitively makes a lot of sense. And all the other things that we're going to look at today, we can refer that back to the backward shift operator. So this is one of the two things that we're going to use repeatedly here on. Another one that I'm not going to use so much is the forward shift operator. Well, going forward is just the inverse of going backwards, right? So we're not going to spend much time on doing that. But of course, if you combine a forward and a backwards, one step backwards and one step forward, you're back to where you started. That's intuition. What is more important, but I wanted to just mention the forward operator because you might see it other places. So this is just to be kind of consistent with other books as well. What is more important is the difference operator, which we call nabla. And it's not, I mean, if you're used to differentiating, it's kind of obvious what you do. If you apply it on a time series, what you do if you look at differences, well, you take xt minus xt minus 1. That is, I guess you've done that already, just without using this notation. So it's just a notation, but this actually means that the definition of nabla, well, the operator you do on xt to get xt, that's the identity operator. So that's just a 1. The operator you need to go from xt to xt minus 1, what is that? Yeah, so it's 1 minus b. So the definition of nabla is just 1 minus b. This we're going to use a lot over the next I would say 5 weeks or so. Another one is the summation. So the summation operator, basically what we have is the sum of all previous elements in the series up to time xt here. So we can also express that as a polynomial in B. We just take the sum of all the previous elements. And if we take the summation and then the difference here, I cannot reach with this. If I take the summation and then the difference, well, the difference operator gives me the sum of xt minus the summation operator on xt minus 1. And it's fairly easy to see, well, that gives us just xt. So the summation and the difference operator are also each other's inverse. And if you do it the other way around, that you take the summation of the difference of xt, you get the same result. Same thing with the forward and backward operator. If you go forward first and then backward, it's the same as going backward first and then forward. It's invariant here. So you have the inverse of the difference operator. We can write it as this is equal to the infinite sum of 1 plus b to, the powers here, which is the sum operator. So that's just a reference to have, but intuition here helps you out a lot. So what I want you to focus on is the difference operator and the backward shift operator. All the rest are, you can say, by default. If you difference things and you want to get back to the original series, well, you just take the summation again. So that's that part. Now, one of the important, the expectation is an operator as such that we discussed earlier on, is that this is again a linear operator. So if you take any of the aforementioned operators and just label them h, so you can insert any of those instead of h, then if you apply that on a weighted sum of some things, you can apply them. You apply the operator on the series and take all the constants out. And you apply them individually on the different series that are in there. And you can also combine operators into new operators. So you can make the power series here, where you define it as a function of set in this case. If you insert b, that's what you have. So you could define, we could define the summation previously we defined it as 1 plus b to the second power plus, but I would say that this is nicer. We have it I equals 0 to infinity, b to the I power, where per definition, if you take b to the 0 power, that means you're not moving anywhere. So that gives us a 1. This is similar to what we have up there. Just all the a's are 1s throughout. Is that a question?
Should it just go to t?
You could go to t. But I don't think if you go to t, you could say yes. But often I will tend to say if you have an infinite sequence. Now we go to stochastic processes in general and we say it's been living there for eternity. And now we just start looking at it. So sometimes I will go to infinity just because if I do not go to infinity, this down here does not hold. You see that? So that's the reason why I do it here. But you can say, in practice, you would only go to t when you do the summation. And you only do the difference starting from the first observation. So you don't have a difference relating the first observation to the one before that because you don't have it. So there's always, in real life, there's always the small twist about the beginning of time. And you can, of course, operators by combination of operators. So there's a lot of things that you can do to combine these operators and write them, you can say, as set, where you can insert anything in here. This is basically what I just, a part of what I wrote up here. But you can also say that you go up to some time point, be it t. Here I will use q, because we'll do that later. And define this operator here that is 1 plus some parameter times the observation before, plus other parameters down to theta q, down to the observation q time steps before. This notation we will use, I mean, it is countable the number of times, but we'll use it a lot in the near future. Basically, probably the one that we'll use the most. But it is essentially just here, and I could write anything in here than b, but as I said, b is the one that we're going to use as reference everywhere, and then sometimes a difference operator as well. So if you just have a good feeling for b and nabla, then you're home safe and can grasp what happens here. If I were to make an example, let's just make a small theta of b polynomial, be it 1 plus 0.4 b plus 1.2 b squared. And if I apply that on, what should I take? I will take this operator and I will apply it on some noise observation. So I have a sequence of epsilons here, just to have some noise. It could be x's, could be anything, just a time series of some kind. What I get out is, well, I get a 1 operating on epsilon t. That's just epsilon t, plus I have a constant 0.4, and then I have b on epsilon t. Well, that's epsilon t minus 1, plus 1.2 times b to the second power on epsilon t. So that will be times epsilon t minus 2. So that's how it's going to work. And I will say over and over again. Just to make things a little bit more complicated, we have the so-called Crochet Product, or the discrete convolution. You define multiplication with this star symbol of operators. So you take two operators and multiply them, or make a convolution of those two to get a new operator. And if you look into the new operator here, how do you get to that? Well, consider it this way. Consider it, if you have the backward shift operator in mind, then it's not so difficult. This pi operator over here that we're constructing, it should have something at lag 0. It should have something where there's no power of b. So that will be the first coefficient in both of these two here, because there's no other way to get that. Now, if you go to, I want to see something for b to the first power here. How many ways can you do that? You can take this one here and shift that one step and keep the non-shifted from the other one, or reverse. Does that make sense? I need a few more nodding. Yes?
Lambda and psi, are they operators or time series?
Operators.
Okay.
So they are operators, say, of, let's say, this form. Or we say that form. So that means all you have to do is to, for any pi here, you have to look into how many combinations of, you say, the powers of b, if you consider it an operator of b, where you can get to I. So that will be I and 0. It will be I minus 1 and 1, I minus 2 and 2, and so forth, until you get to lambda 0 and psi I. So you just have to make the sum of the shifts to be the I that you start off with there. That's the intuition. I think that if you just consider it the backward shift operator, you multiply two polynomials together. If you just treat this b as something, a variable in a polynomial, it's easy to multiply this polynomial with another polynomial. And when you do that, what you get out is another polynomial, right? And that's effectively the same thing we do up here. We just look at how to get to the first order, second order, and so forth in B. So this is just the definition here of the operator lambda of h, psi of h, pi of h is basically what I just said. If you multiply those two together and get pi of h, then it satisfies this Crochet product or convolution. I'm not going to use this abstract notation quite often, but it's good to just know that basically what you do is just multiplying polynomials together and looking at things that have the same order. And you've done that since, I don't know when, probably, maybe not before high school, but you've done that, I know that, repeatedly. So what we've covered today is to get to the local trend models, where we have the weights in here. We do some iterative updates here, and we remember not to invert until we have sufficient number of observations in the sequence here. And then I just added the backward shift operator and the difference operator. I think those are the essential things to remember from today. What I did not add in here are the, you can say, estimators of sigma, but I had a small partial summarize in between. I had a couple of questions in the break regarding the assignment where I want to make, you can say, one answer to everyone. So let me just see if I can easily open that. First of all, I wrote out a message yesterday that you should not use observations from year 2015 and 16 when doing the estimations. You should only use that as out-of-sample controls. So when you make the predictions, you can compare with that. Thank you to the one who wrote that to me and asked that question. Another question I got today was regarding all the other questions here. Which plots to include? What is expected? I think the first one is obvious. You plot the data. The second one, actually, I won't comment on that. When you fit a linear model, you want to plot what the model is like. I think that's also obvious to everyone. Where it's not explicitly given is for question 1.4 and 1.5. So I'll just, and the answer here is the same in both cases, but I won't show you the solution to that because that'll be cheating. And I shouldn't cheat. So basically, what you have is some observations, and then you have some future observations out here that you do not include. So this here, that's year 2014, fourth quarter. That's what you're supposed to do. And then you are directly asked to predict the apartment prices for all of 2015 and the first quarter of 2016. That's all that is available online right now. And then, so that will say what you need to do is to make an estimate from this point and out in the future. But it also says plot the estimates along the entire series and make a table of the predictions. So you need to make some estimate that goes all the way along and makes a prediction here. I don't expect your prediction to be wiggling like this, but not just, this was just not to give you any information about what I expect. So also for question 1.5, well, sorry, but you can make the prediction by just standing at the last point and then making an estimator of what is the prediction. The same thing you can do for the question 1.5, where you use a local linear trend model that we discussed today. You can make the prediction by only considering this point set n equal to this 92-ish, and then just make the prediction. Fit the local linear model, looks like this. However, I do encourage you to also plot the estimate along the entire series as well. So similarly, I did ask you to, whenever you can make a prediction here, make these linear models on the way, show the predictions that you have every time. The reason why I ask you to make all the one-step predictions, of course you should not draw, as I started doing here, 100 lines, because if I draw 100 lines, full length like this, and you make that plot, is that informative? Not so much, right? So you should not do that. What you should do would be to show what are my predictions for each of the observations that I have. That is what makes sense. That is also what you're going to need when you go, for question 1.6. Optimize one-step prediction errors and disregard the first 20 one-step predictions as a burn-in period. Well, you disregard the first few, but then you look at all the prediction errors in the end. But you need to kind of get the system running where you get all the one-step prediction errors. So if you did question 1.5 right, 1.6 is not so difficult. You don't have to find the optimal value by using an optimizer. You can just make a plot for various values of lambda and say what is the relevant S of lambda for this to show what is the good value. And then you should pick an appropriate value from that. And then I mean, if you have time, I should phrase it differently. If your code is well organized, it's fairly easy to, rather than going to the fourth quarter of 2014, to just stop in 2006, as in before the financial crisis, and see what will then happen. And the last one is just, you can see some general comments. Are there any other general questions?
To what extent do you want distinct answers to the same question? The first three, they're very similar.
You don't have to make a new plot for adding a line to it. You can just say, you can see it in figure 1.1 or figure 1. You have the data, and then you add the other thing to it. No, you don't need to make additional plots. For correcting this in the peer grade system, in order to give you a fair chance of doing it, I will create a reference solution to this, where I will have the plot repeated. It's not that I expect you to have that, but just so this is what I expect at various points. Also because in the peer grade system, when I ask you to predict 5 points, I cannot make a nice table in there, so I'll make a table externally, where I also, as a measure of uncertainty, I will give you the standard error, I will give you the variance, I will give you the lower and upper quantiles, say for a 95% prediction interval. So I will try to do it so that it's easy for you to correct, and you should not be in doubt about what is right and what is wrong. There will also be things where you have to say, well, how good is this relative to what is expected? I noticed in the peer grade system, for those, not so many of you, but I did not expect that handed in the test case, I hope it worked out fine. I haven't had any questions in that regard, at least. There was one person who uploaded just some R code, which did not include any results. And of course, you cannot evaluate that. You have to somehow produce the results so you can show the graphs and show the numbers. You could, of course, if you were very nice, copy the R code and execute it. But that's not what is expected when you are going to evaluate something. It should be presented so that you can evaluate it. I also noted that quite some of you who handed in did a good job in evaluating and peer grading each other's, but there were also some that did not peer grade. I'm not going to be harsh on that for the test case, but when we go to the real case, it's actually a learning objective to go in and look into what other people did and kind of assess that to say, is this good or bad? There is an option that I have not ticked in. I've considered it, but that is, in the system, I can say that you should also evaluate or grade your own assignment. Has anyone tried doing that? How do you feel about doing it?
It's odd.
It's odd? What is your comment?
Yeah, I think it's difficult because otherwise you would have included the mistakes you.
I feel the same, essentially. It's odd. For some of the things, it's very easy, because right or wrong. But when you say that, how good is this on a particular, from A to Z or whatever, it's very difficult to do on your own. Yes?
But still, I think it's quite nice that sometimes when you give an answer, you're not completely sure, and sometimes you're, like 95% sure that it's, the right answer. So it's like, okay, I'm sure about, the first half, and then the second half is maybe, above, and so you give like an estimation.
And how should I interpret what you just said? I understand what you say, but is that a, yes, I would actually like to do it, even though it's odd to evaluate my own?
No, it was just an explanation.
Yes, okay. Yeah, but my challenge is to ask the question in such a way that when you did something partly right, you should get some credit for that. It's not just wrong. There might be actually some good parts in there. And that is sometimes a challenge. I will take that. I'm working on that part right now. But I won't do it. But just if those who have tried it said, yes, I really like doing that, then I would tick that. But otherwise, I will not tick it. But you are supposed to peer grade 3 other assignments. Yes?
How long do you expect it's going to take to do the peer grading?
Yes. Let me put it this way. Previously, there were 5 assignments, and I expected you to use 8 to 10 hours per assignment. Now I cut away 1 assignment, and now you have to peer grade 4 times, which means that you have roughly 2 hours each time to peer grade 3 other assignments. So a bit more than half an hour is, and I can say when I correct assignments myself, let me put it this way. First of all, I'll give you, at least in my view, a very well kind of written, this is what I expect. It's not going to be long. It's going to be a little bit condensed, but if you know what to look for, it should be clear what I really want. And I'll have someone else than myself to read through it before giving it to you. Because I hope that, I think that is needed. Because otherwise we end in the same situation as you do, but I meant that when I wrote it, but when someone else read it, it's like, it's not clear. So I use, typically I set aside 20 minutes per assignment for correcting. And you can say a large part of it is reading. So half an hour for each of them is what I expect. And I think that's fair. If you end up saying I spent way much more time, let's have a discussion about that. But I would like to do it first and then take the discussion after that. But I do expect that you use about half an hour, a little bit more than half an hour on each of them. There are some that are easy to correct, and there are some that are difficult to correct. The one thing that kind of makes me use long time correcting things is when I dig into the code. I don't expect that you go into someone else's code and figure out what is going on in there. But that's where you also have the chance or the opportunity, if someone did not see that you actually did something brilliant and that they gave you a low score, you can object to the grade that was given, and then I will go in and look into those. But usually when I comment, give feedback to assignments the same way, most do know what they did right and did wrong, sort of what you said. The gut feeling is like, these parts are, they're just poof, the way they want it to be. And then there are other things where, I hope this is not too bad. Is that the diplomatic way of saying it at least? Other questions? Yes?
Do we also have a deadline to when the peer grading should be done? If we hand it like Thursday next?
Yes. I've set the deadline to be, I think, the following Thursday night. So to give you a full week. I think that was fair. It could be less. The disadvantage of doing that is that I will, of course, when there are flags, it's called, I will probably resolve them during the week if they are there. But then I won't have time to look into the last ones before we meet again next Friday. The following Friday, yes?
About the assignment, in question 1.5,
What is the?
forgetting factor. We use lambda.
Yes, this is the same as before.
Okay.
1.8, 0.8. I could write that and update it again. I will do that to make it clear. Thank you for asking that. Yes?
For question 1.3, do you just mean fit a line, or do you mean something more elaborate general linear model?
I say fit a line. Okay. Yes. It says simple linear regression.
Yeah.
That is fit a line. One intercept, one slope. Yes?
In question 1.3, when you say all the data, is it the year 2014?
Essentially 2014, but it won't hurt anyone if you use all the data, but only including for 2014. That was why I wrote it as a general comment up here. Use only these. do not use observation from 2015 and 2016 for estimations. To be a global comment for all of them. But to be honest, I don't think anyone will notice. Other questions? I might if I read the code, but not without reading the code.
In 1.7, or to change something in the model, I don't understand. The forecast method is when
The forecast methods are the method that you have applied up here.
okay, so models in
Can you think of something that could be a good extension of what you've done so far?
okay.
It's a very open question. It's one of those that is difficult to assess. It's one of those that I probably have to read a few of. Okay. Otherwise, I think it's time to do some exercises. And if you have individual questions related to the assignment, after 11:30, I'll be happy to answer those. But till then, I mean, I suggest that we focus on the exercises also because there are some links between the exercises and the assignment. Good.